What is AI, really? If you strip away the buzz, the hype, and the science fiction, it comes down to this. AI is software that takes in information and produces an output that helps change what happens next. It might make a prediction, suggest a movie, answer a question, spot a face, or recommend the next step in a process. That sounds simple, but it explains almost everything. And here's the big thing to remember from the start. AI is not magic. It is not a brain trapped inside a computer. It is a set of methods that help machines recognize patterns, learn from examples, and make useful predictions. So how does that actually work? The easiest way to understand modern AI is to split it into two phases: training and inference. Training is when the system studies lots and lots of examples. It looks for patterns, adjusts itself, and slowly gets better at a task. Inference is what happens after that, when the system uses what it learned to make a new prediction on fresh input. Think of it like this: training is practice, inference is performance. If you show an AI thousands of photos labeled cat and dog, it doesn't memorize every image like a person might memorize flashcards. Instead, it learns which features tend to go together. Maybe it notices ears, whiskers, shapes, textures, or even tiny patterns too subtle for us to describe easily. Then, when it sees a brand new image, it asks, what is this most likely to be? That same basic idea powers a huge range of modern AI. Systems can classify spam, translate language, recognize speech, forecast demand, and rank search results. Different tasks, same core idea, learn from data, then use that learning to make a decision. But AI did not begin with giant datasets and powerful chips. It started much more simply. In the early days, many researchers believed intelligence could be built from rules. If you could write down every important rule, the computer could follow them. This became known as rule-based AI. A classic version was the expert system, which combined a knowledge base with an inference engine. In plain English, that means one part stored facts and another part applied if-then rules to reach conclusions. These systems worked best when the world was narrow and stable. One famous success was XCON, a configuration system used by Digital Equipment Corporation. It helped assemble complex computer orders and reportedly saved around $40 million per year. That was a huge reminder that even early AI could create real value. Still, rule-based AI had a weakness. The world is messy, human knowledge is full of exceptions, and writing every rule by hand quickly becomes impossible. Long before the term artificial intelligence became famous, Alan Turing posed a deeper question in 1950. Can machines think? He turned that philosophical puzzle into a practical test, asking whether a machine could hold up in conversation well enough to seem human. That idea mattered because it shifted the field from abstract debate to real experiments. Then came 1956, often treated as the official birth of AI. At the Dartmouth Summer Research Project on Artificial Intelligence, researchers like John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon helped give the field its name and its ambition. The dream was bold. Maybe machines could do more than calculate. Maybe they could reason. Soon after, researchers began exploring learning machines. In 1958, Frank Rosenblatt introduced the perceptron, an early neural model that could learn simple patterns from examples. This was exciting because it suggested a new path. Instead of only programming intelligence, maybe we could grow it from data. But early neural networks had limits. In 1969, work by Minsky and Papert showed that single-layer perceptrons could not solve some important problems, such as XOR. That critique slowed neural network research for years. It was a painful moment because it showed that hope alone was not enough. The math had to catch up. And that pattern would repeat throughout AI history. Big promises, hard reality, then another breakthrough. In the 1960s, one of the first chatbots, Eliza, amazed people by mimicking a therapist with simple language tricks. It was not truly understanding, but many users still felt understood. That tells you something important. Humans are quick to see intelligence, even when the system underneath is simpler than it appears. Then came the first AI winter, and later another one. In the 1970s, and again in the late 1980s and early 1990s, funding and excitement cooled after overpromises, fragile systems, and disappointing results. Expert systems were powerful, but expensive to maintain. Promises were bigger than reality. The field had to reset. The next major shift came from a method that changed everything: backpropagation. In 1986, a landmark paper showed how to train multi-layer neural networks by sending error signals backward through the system. That gave researchers a practical way to improve deeper models, not just simple ones. This was one of the most important turns in AI history because it made learning more flexible and more powerful. Still, progress was gradual until AI started winning in ways everyone could see. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov. That matchup mattered not because chess was the whole future of AI, but because it proved machines could outperform elite humans in a highly complex domain. People could suddenly feel the reality of machine intelligence. But the real explosion came when AI met data at massive scale. The ImageNet project helped standardize image labeling, and by 2012, the competition built around it became a breakthrough moment. AlexNet, a deep neural network, crushed the field with a top 5 error rate that was more than 10 percentage points better than the runner-up. In practical terms, it was a wake-up call. Deep learning, big data, and GPUs had changed the game. After that, AI stopped feeling like a niche research topic and started becoming a platform. Then in 2016, AlphaGo beat Lee Sedol in a 5-game match. Go had long been considered too intuitive, too subtle, too human for brute force methods alone. But AlphaGo combined learning with search and showed that AI could master problems once thought out of reach. The next leap came in language. A paper called "Attention is All You Need" introduced the transformer architecture. That one idea made it much easier to train large language models effectively, and it helped launch the modern era of chat-based AI. Suddenly, systems were not just classifying images or playing games. They were generating text, summarizing ideas, translating languages, and helping people write. By early 2023, ChatGPT had reached roughly 100 million monthly active users in about 2 months. That kind of growth was staggering. It told the world that AI had moved from the lab into everyday life. And now, AI is everywhere. It helps filter email, power search engines, suggest videos, detect fraud, improve maps, support medical analysis, and assist in customer service. In business, adoption has surged. A 2024 McKinsey survey found that many organizations were already using generative AI regularly. At the same time, another challenge became clear. The hard part is not just building AI. It is proving that it creates real value. That is the most important lesson in the whole story. AI works when data is good, goals are clear, and the system is measured carefully. It is not a magic box. It is engineering, statistics, and computing power working together. So when you hear AI, don't think mystery. Think pattern recognition. Think training and prediction. Think a long history of people trying, failing, learning, and trying again. From Turing's question to Dartmouth, from rule-based systems to neural networks, from winters to breakthroughs, AI has always been a story about making machines a little more useful, a little more capable, and a little more human-like. And the story is still being written. Try a simple AI demo and describe training versus prediction in 1 sentence below.